and we are going to take a look at 4.3. If it will scroll down for me. There it is. The binomial distribution. Okay, so the binomial distribution is a specific type of discrete probability distribution. Okay, it's pretty easy once you get the hang of it. The formulas are fairly simple to calculate. So a probability distribution must meet, okay, in order for it to be a binomial distribution, it must meet the following characteristics. So the first one is that there are a fixed number of trials. Okay, so 10 trials, 100 trials, it's a fixed number. The next one is there are only two outcomes that can happen. So two possible outcomes. So you're looking for something specific to happen, and in that case, those outcomes are going to be success or failure. So let's say I want to find the probability that I am choosing out of all of my students, a dual enrollment student. Okay, so I say that's my probability. So it's either you're dual enrolled or you're not dual enrolled. So its success would be the dual enrolled, the failure would be not dual enrolled in that case. Okay, we're going to denote success as P and failure as Q. And then just look down at this note here, because success doesn't necessarily mean success, and failure doesn't mean like you're losing. It just means the probability that something is happening. Okay, so for a binomial distribution, the random variable x represents the number of successes out of n trials. The term success does not necessarily mean it's a good outcome. It's just the outcome you're looking for. So if I'm looking for heads, okay, heads would be success, tails would be failure. Okay, but then if I was looking for tails, it would be the other way around. So it's just success is just what you're looking for, and then failure is not what you're looking for. The last one is that the trials are independent and they will remain constant. Okay, so trials are independent. Okay, so P and Q, and then P and Q will remain constant. So each time I do the trial, P is the same. The probability is the same every time. So if P and Q are the same every time, then if I add them together, I'm going to get 1. Okay, so those are your stipulations for a binomial distribution. Another thing here, just to tell you, these are also, you might see it called a Bernoulli trial. So Bernoulli. So instead of saying in a binomial distribution, it might say a Bernoulli trial was ran. Same thing. Okay, your formulas, like I said, they're fairly simple. The mean, or the expected value, is just n times p. And then the standard deviation is just the square root of n times p times q. So remember, p is the probability of success, q is the probability of failure, n is the number of trials. So if we look at example 3.1, we can just pick out some of that information. Missing some stuff here. Okay, so it says approximately 70% of statistics students do their homework in time for it to be collected and graded. Each student does homework independently. In a class of 50 statistics students, what is the probability that no more than 5 will do their homework in time? Students are selected randomly. So is this a binomial experiment? So are there a fixed number of trials? Yes, 50 students. Okay. Are there two possible outcomes? Yeah, they either do their homework or they don't. Okay. Are the trials independent? Well, it says there, each student does their homework independently. So yes, this is a binomial experiment. Okay, how should the random variable x? So x is going to be how many, what we're looking at. So what we're looking at in these 50 students is how many students do their homework on time. So x is going to be the number of students that turn in their homework on time. So in this instance, success would be that the student does their homework. Failure would be the student does not turn in their homework. Okay, what values can x take on? So out of those 50 students, you could have 0 students that turn in their homework on time. You could have 1 student that turns in their homework on time. 2, ... all the way to 50. So x can be 0 through 50. All right, and this says what are the values of P and Q? So P, so what does it say up here? Approximately 70% of statistics students do their homework on time. So there's your P, 70%. As a decimal, 0.70. Which means Q is the percent of students that do not turn their homework in on time. That's not given, but we can find it. What is it going to be? 30%, because if 70% turn their homework in on time, 30% do not. So 1 minus 70, 30. All right, and then F says to translate the probability statement that no more than 5 what is it? Will do, what is the probability that no more than 5 will do their homework on time? Okay, so the probability here, translate no more than 5, it's probability that x is no more than 5, so it has to be less than or equal to 5. So that's your probability statement, that x is less than or equal to 5. That would be really bad. No more than 5 students turning their homework in on time. Hopefully that probability is very low. But I'll show you how to find it on the next page. Okay, so here is the formula for computing probability with a binomial distribution. All right, so you have P of x, so the probability of x is going to be, you have n cx so the combination formula, times p to the x times q to the n minus x, and this will be on your formula sheet. Okay, then it's telling you n is the number of trials, p is the probability of success, q, probability of failure, x, the number of successes, and minus x, the number of failures. All right, this is not, let me see if I can get this to copy over a little better, because I want to see the chart. Where's my mouse? There it is. Chapter 4. See if I can bring that up here. Nope. All right, I'm just going to bring it over here just for the purpose of the notes when I upload those. All right, there we go. All right, so we have, according to a Gallup poll, 43% of Americans support a universal basic income program, UBI. Suppose 3 Americans are randomly selected. Let X represent the number of Americans in the sample that support UBI. All right, so first we're going to determine the values of N, P, and Q. So N is the number of trials, which is how many people I am looking at. So I'm selecting 3 Americans. P is the probability of success, which in this case is I'm asking them, do you support the UBI program? And they say yes. Okay, so that's what I'm looking at. So that is right here, 43%. Okay, then Q is the probability that they say no. So for Q, I'm going to do 1 minus 0.43, so 0.57. All right, then I want to construct the binomial distribution for this. So I'm going to go here to X. So X can take on 4 different values. You could say that 0 of them say yes, 1 says yes, 2 say yes, or all 3 say yes. Okay, then we're going to do the probability using our probability formula before I show you how to do it in your calculator. Okay, so we'll do for 0, you have NC0, so we're using the formula here. So N is 3, C, 0. Okay, that's first. Then P to the X. Okay, so 0 in this case is our X, so 0.43 to the 0. And then Q to the N minus X, so, oh, I have to actually write what Q is, sorry, 0.57. So 0.57 to the 3 minus 0. Okay, so do we remember where to do the C in our calculator? Math. So I would do here 3C0, so 3 math over to probability, NCR, 0. That's just going to be 1. Okay, so this is going to be 1 times, what's anything to the 0 power? No. 1. Anything times 0, 0, anything to the 0 power is 1. And then 0.57 to the third. So 0.185. So 1 times 0.185 is 0.185. Okay, so the probability that 0 people say yes, 0.185, or about 18, 19%. All right, let me get a different color for 1. All right, now we're going to do 1. So you're just replacing the 0 in this formula with a 1. So 3, C1, 0.43 to the first, 0.57 to the 3 minus 1. Okay, so I'm going to get my calculator out, and I'm going to go 3, math, prob, and CR1. It's going to be 3, and then I'm just going to go times 0.43 times 0.57 squared. 3 minus 1 is 2. And that's going to give me 0.419. All right, we'll get a new color for 2. Do the same thing. Replace the 1 now with a 2. So 3, choose 2. 0.43 squared. 0.57 to the 3 minus 2. So 3, choose 2. So 3, math, probability, and CR2 is 3. Then we're going to go times 0.43 squared times 0.57 to the first, so just 0.57. So that is going to give me 0.316. All right, and then the last one for 3, we'll go 3, choose 3, 0.43 to the third, 0.57 to the 3 minus 3. So 3, math, probability, and CR3 is 1 times 0.43 to the third, 0.57, 3 minus 3 is 0, so that's just 1 there. So it's just 0.43 to the third. So 0.079, well, 0.080, or you could do 0.0795. It's up to you. We'll do 0.08. So see this? It goes up, 0, 1, 2, 3. This goes down, 3, 2, 1, 0. Okay, now let's go ahead and add what I have in the chart here just to make sure. This should add up to 1. So, or close to it. So 0.185 plus 0.419 plus 0.316 plus 0.080. I don't know why I wrote a 1 there, but it should be a 0. So it adds up to 1. So we have a valid probability distribution. Now, we're even using some calculator commands there with the C, but I showed you guys the formula on how to do that, right? Remember, it was n factorial over n minus r factorial. Okay, imagine before they had calculators that did all that. Okay, they had to do all that on their own. And there's an even easier way to do this, which I'll show you with the next problem. But let's answer the rest of the questions here. Okay, so we did part B, we construct the binomial distribution. Now we want the mean and the standard deviation. So remember those formulas. The mean is n times p. So the mean is going to be 3 times 0.43. So let's go ahead and do that. This is kind of big here. So 3 times 0.43, 1.29. And then the standard deviation is the square root of NPQ. Okay, so that's the square root of 3 times 0.43 times 0.57. So we'll put that in just like that. So square root 3 times 0.43 times 0.57. Get 0.857. Let me redraw that box because you can't see the one. Okay, so what this means, there's the probabilities, but the mean and the standard deviation means, okay, if I ran this experiment picking 3 random people, okay, I don't know, 400 times, on average about 1.29 of them would answer yes, with a standard deviation of 0.857. Okay, then part D. What is the probability that exactly 2 of these Americans support UBI? That's just right here, this 0.316. And then what is the probability that at least 1 of these Americans support UBI? So that would be the probability that X is greater than or equal to 1. So you could take that and add these 3 probabilities, or you could just do 1 minus P of 0. So 1 minus 0.185, which would be 815. All right. Let me show you guys how to do this in your calculator. Actually, yeah. We'll do it with the next example because we got a lot more examples here. Okay, for your calculator, write this down here and then we'll do it with the next example. So just write the instructions. You're going to go to second, and then you're going to go to distribution, which is the second of vars. You are going to find binom PDF. And then it's going to ask you number of trials, probability, and X. So we just say here, N, P, X. And then we're going to hit enter. Okay, so let me just show you where that is. We'll just check the probability of 0 on this first example. Okay, so see where it says vars right underneath the arrows to the left of clear. So second vars is that distribution. So these are all your distributions. I usually would scroll up actually and go backwards. It's A in the 84. So binom PDF. I'll show you what CDF means in a little bit, but right now it's PDF is just a single probability. Okay? And then it's going to say trials. So trials was 3, P, 0.43. And let's look at the X value 0. Paste. And then it does it for you. So it does that entire calculation for you. Okay, so let's look at this next example. So according to, let me get this copied over real quick. Hold on. There we go. Okay, according to Pew Research, 10% of Americans do not use the internet. Suppose 10 Americans are randomly chosen. Let X be the number of Americans in the sample that do not use the internet. Okay, so let's identify our variables here. We have N, number of trials. We're choosing 10 Americans. P is the probability that they do not use the internet. Okay, so that is 10%, 0.10. Q is the probability that they do use the internet. So that's 0.90. And then we want to construct this probability distribution from 0 to 10. And I'm not going to give you guys any more than 10. Now you can do the Binomial PDF for each one of those, but there's an even shorter way to do this. Okay, so I'm going to show you guys that. I'll let you get this copied in. We are going to use a list. Okay, so get your calculator. Go to your list. So remember that's stat, and then edit. All right, so I have some stuff in here. I'm going to go to L1, and I'm going to go up, and I'm going to clear it. And I'm going to enter 0 through 10 in here. Okay, so you're going to put the X values in the list. All right, once you get the X values in list 1, go over to list 2. Go to the top where L2 is highlighted and hit clear. Enter. Go back up to L2. So this is the key here to getting us in everything. So go back up to L2, and then you're going to go to your binomial distribution. Okay, so make sure L2 is highlighted. Then go second, distribution. Then you're going to go up to Binomial PDF. In Binomial PDF, you're going to put this in. So trials are 10. P is 0.10. The X value is L1. You're going to have to put each of those in. So second 1 for L1. Paste. Enter. Enter. List is filled out for you. So let me show you that again. Okay, so I'm going to go up here and I'm going to clear this. Once you get 0 through 10 in your list on L1, go to L2. Make sure L2 is highlighted. So right here it's not highlighted, it's in my first column. So I need to go up here. See where it's highlighted? Then once it's highlighted, then you go second, distribution, go up to Binomial PDF, enter, trials is 10, P is 0.10, X value is L1. So for L1, go to second 1 to get L1. Paste, enter, enter. Okay, so that is going to give you this, this list filled out. And I'm going to copy these over. And if I'm just looking at this real quickly, when I get down to 6 and down, so this, remember scientific notation we talked about last class? So 1.4 e to the negative 4, so that's over 4 places. Then this is over 6 places, so this is 7 through 10 is just going to be 0 for that one. Okay, once it starts going more than 4 places over, it's just a probability of 0. So when I'm filling this out, it's going to look like this. I've got 0.349, 0.387, 0.194, 0.057, 0.011, 0.001, and the 6 was a 1.4, so 0.0001, and then 7 through 10 are just 0. All right, so the binomial probability distribution is complete. Now we're going to answer some questions about it. So B, find the probability that exactly one of these Americans will not be an internet user. So this is going to be P X equals 1. Because remember, the success is that they're not an internet user, because that's what we're looking at here. So that's just this right here, this 0.387. Okay, find the probability that 3, 6, or 9 of these Americans will not be internet users. So, for the or is adding. So we would take the probability of X equals 3 plus the probability that X equals 6 plus the probability that X equals 9. And we're going to add those together. So 3 is 0.057. 6 is 0.0001, and 9 is 0. So if I add all of those together, that's 0.0571. Okay, find the probability that at least one of these Americans will not be internet users. So remember, at least, that's probability that X is greater than or equal to 1. Okay, well, if I look at that, then it's all of these probabilities. Or I could just subtract 1 from 0.349, which is what I'm going to do. So I'm going to go 1 minus 0.349, which is going to give me 0.651. Yeah, so for the number 6, it was 1.4 e to the negative 4, which means this went 1, 2, 3, 4. So it was 3 zeros and then a 1. Okay, and then the last question, find the probability that at most 8 of these Americans will not be internet users. So at most 8, which means less than or equal to 8. Okay, but if I look at that, that would be adding all of this. So you're just leaving out 9 and 10, which is 0. So this is just 1. 1 minus 0 is 1. Okay, now let me show you another function in your calculator. Let's say I had that and these two were not 0, and I wanted to find the cumulative probability. So if you have a less than or equal to on here, you can find the cumulative probability. So for a less than or equal to, then that would be a cumulative probability. Okay, because you're adding up all of those values. So instead of binom PDF, you use binom CDF, so C for cumulative. Okay, so you would go binom, so second, distribution, and then you're going to pick binom CDF. And then it's the same thing, NPX. Okay, but what it does is it's going to add the values from 0 to x. So that's what that does. It adds values 0 through x. So if I did that with the 8, oh, it's on the other screen. Hold on, bring it over here. Okay, I would come over here. I gotta get out of this. So I go second quit, go to my home screen. I'm gonna go second distribution. I'm gonna pick the binom CDF. Trials are 10. P is 0.10. X value I want is 8. I wanted to add 0 through 8. Rounds to 1. All right, last thing before we do some practice, and then I'll come around and help you guys with your calculators. is the shape of a binomial distribution. So just maybe some homework questions. Okay, so just depending on the probability. All right, so if the probability is exactly 50%, then it's going to be symmetrical, so it'll be normal. So if p equals 0.5, binomial distribution will be symmetric. If it is greater than 0.5, it's going to be skewed left. And if it's less than 0.5, it'll be skewed right. So for these examples here, a probability distribution looks like a histogram, so a bar graph where they're touching. So, yes, histogram's touching, bar graph's not, I believe. Okay, so if we have number of trials is 5 and probability is 10%, that's less than 0.5, so it's skewed right. So then we could say it looks something like this. 1, and this goes up a little bit, but then it just skews really low. Maybe like that. So it's skewing to the right, meaning it goes up here, and then it's got a tail to the right. Then for the second example, you have an n of 6, probability of 0.8, which is greater than 0.5, so this is just going to be the opposite. It's going to skew left. So it'll have its smaller tail over here. Maybe something like that. And then it starts getting bigger. Like that. So it skews to the left. And then the third example, you have an n of 8, probability of 0.5, so that's symmetrical. So that would be a normal distribution. So it is a histogram with 8, 1, 2, 3, 4. Then this should be the same, 5, 6, 7, 8. So we're going to like that, nice and normal distribution. Okay, so I have some practice problems for you guys. I'm going to have you go ahead and try those. Okay, let's go ahead and go over these. So number 1, we have an insurance company has estimated the following cost probabilities for next year on a particular model of car. And then we want to find the expected cost to the insurance company. So the first thing that we need to do here is we need to finish filling out the probability table. So I am going to move this so I can see it. There we go. Okay, so I have my probabilities 0.6 plus 0.05 plus 0.13 is 0.78. So the remaining probability is 1 minus 0.78, so 0.22. So I'm going to fill that out here. Okay, because all the probabilities have to add to 1. And then the expected cost is the expected value. Okay, and the expected value is just the mean. Okay, so expected value equals the mean, which is the sum of x times p of x. Okay, so we need to do x times p of x. So I need to do 0 times 160. Okay, so 0 times 60 is 0. 500 times 0.05 is going to be 25. 1,000 times 0.13 is going to be 130. And then 2,000 times 0.22 is going to be 440. So it's the sum of these values. So 0 plus 25 plus 130 plus 440. So 25 plus 130 plus 440 is going to give us 595. So the expected value to the insurance company, so over time, for this particular model of car is going to be about $595 for the expected cost. All right, number 2 is a little more subjective. So imagine taking a 10-question true-false exam. You randomly guess at each question. Is this a binomial setting? Yes. Okay, so you have independent, each question is different. 10, fixed number of trials. Probability of success, 50%. Failure, 50%. So yes. How many questions do you think you'll get right? All of them? What do you got? What else? 7? 5? 5? What's the strategy? Are you going to go A, B, 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 A? How are you going to do it? Or true, false, true, false? All true. So technically, if you want to have greater than or equal to 5 questions, there's really no right answer for this one. But if you want to have greater than or equal to 5, you need to pick either all true or all false. All the same every time. That way your probability is constant each time. Okay, because if you go true, false, true, false, true, false, what if it's false, true, false, true, false, true for the answer key, right? You want to guarantee that you're going to get at least a couple right, unless it's like all true or all false on the exam. And I mean, I would do that just to mess with students, but not most teachers wouldn't. So, you know, technically it should be about 50%, but you got to pick all true or all false. How surprised would you be if you got all of them right? Or sorry, 6 or 10. 6 out of 10. 6 out of 10. Or 6 or better. Sorry, 6 or better. Very surprised? All right, what's the actual, so let me show you how to find the actual probability of this. So if I want to do, that would be the probability that x is greater than or equal to 6, right? An easy way just to do this, a quick probability, would be to do 1 minus binom CDF of 5, okay? So 1 minus the binom CDF of 10, 0.5, and 5, because you would take the cumulative probability of 0 through 5 and subtract it from 1, which ends up giving you the probability of 6 through 10. Okay, so that's what that does there. So that actual probability is going to be, let's see, 1 minus binom CDF 10, probability of success is 0.5, and I want the cumulative value of 1 through 5. So 0.377 is that actual probability there. And then how surprised would you be if you got an A? 9 or 10. Very surprised. So that probability, you could do 1 minus binom CDF for 8, but probably easier here if I just did the PDF of 9 and 10. So binom PDF of 9, so the probability of getting 9 right, plus the probability of getting 10 right. So that would be 10, 0.5, and 10. So let's see what those actual probabilities are. So if I go here, so 10 trials, probability of success is 0.5. So let's see for 9. The probability of getting exactly 9 right is, we're going to go 4 decimal places out here, 0.0098. Less than 1%. Probability of getting 10 right, exactly 10 right, so 100%, so we're just going to change the x value here to 10, is 9.7. So we're going to go 9.7 times 10 to the fourth, or e to the negative 4. So 1, 2, 3, 4. So 0.00097. Or was that 9.8? It was 9.8. Okay, so if I add these together, .0101. So that's that actual probability. So about a 1% chance of getting 100%. I'm going to make your next Blackboard assignment something along these lines. All right, let's take a look at number 3. Approximately, or one more note about this one up here. This, I pulled this, I think it was like 2000. This was the first year I graded AP exams. So this was an AP exam question. So it was a little bit harder than what you guys are doing here, but just kind of get you practicing with that and thinking about these things. Okay, so approximately 2% of the nation's children, I think this might be a little bit outdated. I think it's from like 2012 or 14. Approximately 2% of the nation's children have a parent who is in jail or prison. Let X be the number of children that have an incarcerated parent from a random sample of 100 children. So let's verify that this is a binomial setting. So we have a fixed number of trials, 100 children, fixed trials. We have, let's see here, 2 possible outcomes, jail or out or not jail. We've got independent trials. Okay, to confirm that we have independent trials, it really doesn't say here. It says the random sample of 100 children. We couldn't have any siblings in the sample. That's the only issue there. Okay, but it doesn't say it, so we're going to assume we're okay. All right, and then what do we have? P and Q. So P would be here 2%, the probability that parent is incarcerated, which means Q would be 0.98. All right, so P of X equals 0. What does that mean? The probability that out of all 100 children, that out all 100 children, 0 have an incarcerated parent, or none. Okay, so let's actually find those probabilities. So for 0 and 1. So the probability for 0, so what do we have here? So we did P and Q. So N in this situation is just going to be 100. So if I'm doing this, I'm going to go binom PDF. You've got 100 trials. Probability that the parent is in jail is 0.02. And then the probability of exactly 0 out of those 100 trials. So let's do that. We're getting ready to run out of time here. 100. We have here 0.02 and 0. So that's going to be 0.133. Okay, then you're going to do the same thing for the probability of 1. You're just changing the 0 to a 1. So second distribution, we're going to change the x value to a 1. And that's going to be 0.271. All right, so fairly high probabilities there. Okay, because you have more trials. You have 100 trials there. What is the probability that 2 or more of the children have a parent in jail or prison? So it's just the probability that x is greater than or equal to 2. Since I already found the probabilities for 0 or 1, it's really the probability that x is less than 2, which means I could add these probabilities. So add okay, so if I add 0.133 plus 0.271, you get 0.404. 404. There we go. Oh, wait a second. What is the probability that 2 or more? That's the probability that fewer than 2. Sorry, we're not done yet. Where's my eraser? All right, this is still 0.404. Okay, so the probability that 2 or more of the children, this is the probability that fewer than 2 have one, so 2 or more would be 1 minus 0.404. Which is going to be 0.596. All right, we are out of time.